So we're getting ready to talk about significant figures. And if you've had a chemistry course or a laboratory course or a science course in the past, you probably have experienced significant figures and you hate them. You hate them so bad you can't stand it. Well, it's my job to basically lay out significant figures for you to maybe have you have a better relationship with them. That's what this lecture, very short, I hope, lecture video is going to be all about. How do we treat significant figures and what is the importance of significant figures in a laboratory? So significant figures, a lot of people ask why. Why do we have to do this? Why do we have to go through all of this? Folks, it's just a way that we round numbers in a laboratory. That's all that this is. So it's this concept that we're going to go in to a laboratory environment or do some calculations with laboratory type of data. And how do we handle those? We'll get these numbers in the calculator that's got probably 15 different decimals after or numbers after the decimal. So where do we round it? Where do we stop? Is there a rhyme or reason? And can I just say 2 digits after the decimal every single time? Wrong. That's wrong. You can't do that. That's not the way that this works. So we're going to have to understand the concept of significant figures, and then we're going to have to go in and do some calculations with laboratory data and talk about how significant figures are going to be applied to the calculations, whether they're addition, subtraction, or multiplication and division. So significant figures, one of the things that really kind of start this whole concept or discussion is the difference between what we call precision and accuracy. These two things are different and they are not related to each other. So basically, you have seen, if you've taken a chemistry course before in the past, maybe, and some of you have not, and that's okay. I don't ask that you do, but you've seen a picture that looks something like this, right? It's this typical bullseye analogy that they like to use. And in the laboratory, what we want you to do is get laboratory data or obtain laboratory data that is hitting the bullseye and hitting the bullseye every single time. Okay, so this is what we're after. Ding, 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 right up here to the top. We want all of our darts to hit the same spot, and we want them to hit that spot every single time that we throw them. So in a laboratory environment, basically what this means is that if I'm doing a lab and I'm generating some data, that data is going to lead to a number. And this number, we question, is this number correct? The correct is what we refer to as the accuracy. So how accurate is the number? Is it accurate or is it not? So if it's accurate, I'm hitting the bullseye. That's what basically that analogy is going to tell me. So in a laboratory, as I'm working, as I'm generating some lab data, I'm doing some data, some calculations, and I'll get this final answer. Am I getting the proper final answer? Is it where I need it to be? That is the definition of accuracy. And that's hitting the bullseye when we do throw the darts. All right. Now, the other part of this discussion is this idea of precision. And a lot of people get confused with precision and they think that accuracy and precision is the same. And accuracy and precision is not the same, folks. They are not the same. All right. They're not equivalent. You can have one, but you can't have the other. Sometimes maybe you're one of those people, and we don't want you to be one of those people. We want you to throw laboratory darts at the dartboard, and we want you to hit the bullseye, and we want you to hit it every single time. So what is the idea of precision? Well, there's actually two things that we can talk about with the term precision. So the very first thing that I want you to understand is that precision is all about how many number of numbers can I get? Or how many decimal places can I carry the number to? That is a sign of precision in a way in terms of some of these questions and some of the things that we talk about. So for instance, with precision, let's say that I make a measurement and the measurement is just a 2. All right, 2 centimeters, let's say. I measure something with a ruler. Well, someone around me could maybe have a better ruler, and that ruler allows them to report a distance of 2.1 centimeters. Okay, that is a better number. It has more numbers associated with the measurement. And because of that, we can say that this person is more precise than that person. And then let's say someone else has a better ruler, and that better ruler is going to lead to a more precise value. And let's say that this is a 2.15 centimeters. Okay, well, this number has more digits, and those digits basically mean a more precise number or closer to the true value. Maybe, just maybe, but it might not be the true value at all. That's the whole concept here, right? Precision is just about how fine-tuned can you go with the number. How precise is it? So 2.15 is a more precise number than 2.1, which is more precise than a 2. And let's say that there's a fourth person in the laboratory and they got even a better ruler because they spent more money on that ruler, right? And that ruler has more bells and whistles and more things that come along because it's more expensive, and it makes you feel better because it's more expensive. And that person reports 2.156 centimeters. That is a more precise number in terms of how low can we go? How precise, how good do we feel that this is the actual number that we have measured? Actual does not mean the actual real true value of what it should be, because this thing might be 4 centimeters and not 2, and I just don't know how to use a ruler. But I've used a ruler, I've made a measurement. It might not be a correct measurement, and that's okay, but this measurement in this person's case can be carried out to 3 decimal places. All right, so in other words, let's take a look at an image like this. This is a graduated cylinder. And in this graduated cylinder, I've got some liquid. And this liquid, some of you might say 6 milliliters. Okay, well, I hope that you're not my lab partner, because if you look at this measurement and you just want to stop at 6, then we've got some talking to do. All right. But you, as a person that's measured this, can feel really, really good that it's 6 milliliters something. But it starts with a 6. So you're going to put 100% of your money on the Las Vegas table. And you're going to say, I know this is 6 milliliters point something. I just don't know what that point something is. But it's 6 point something. Okay, well, you're a step in the right direction, but someone behind you could come along and say, well, no, you can actually be more precise than that. There's the key word, precise. You can be more precise with that measurement reading, because there's 6, I know that, but you know what? I'm going to put 100% of my money on the table, and I'm going to say that this is actually a 6.1 and a 6.2 milliliters. Ding, ding, ding. Okay, that's good. That's great. You're a step in the right direction. So this basically means that you feel really, really good about putting all of the money that you own on the betting table, and you're going to tell someone that is 6.2 milliliters. I know that for sure. I know it for sure. All right. Then another smart alecky person can get behind you and say, well, I'm better than that. I can do better than 6.2 milliliters. And they're going to come in and they're going to look at this a little bit closer, and they're 6.2, they're 6.3. And they're going to say, you know what? I think that we can round this off. So there's 6.2. It looks like it's a little more than 6.2, but it's not quite yet 6.3. So I'm going to round a number on the back end. And I'm going to say, well, you know, this is not quite half. So this is not 6.25, but maybe this could be a 6.23 milliliters. Or 6.22 milliliters, or 6.24 milliliters. You're trying to increase how precise your number is by tagging on an extra digit. Now, this person cannot go to the betting table and bet everything that they own on the betting table with that last number. That last number has been rounded for sure, right? This is not a concrete actual number. We are rounding it. And the way that I round it might be a little different than the way that you round it. But the thing here is that that very last digit is a rounded number. And folks, there's no way around it at this point. And this is going to lead us into the discussion of significant figures, because what significant figures is, it's a measurement, and these measurements have what we call significant figures in the front plus one rounded number, typically at the end of the measurement, of course. And that's what a proper significant figure is all about, okay? It's how low can we go, how good can we feel about the measurement, and then sooner or later, based on what we have in our hands that we are using to make these measurements with, we are going to have to round it off at some point in time. And that just depends on the tool that we have in our hand. So wherever we round that off, that very last digit is uncertain. So significance can also be called certain digits, and the rounded number is a uncertain digit. So a significant figure will have certain digits and uncertain digits that come along with it. All right. So now with that said, we can go through this concept of significant figures maybe a little bit more. So we've said we've got precision and we've got accuracy. Accuracy is basically hitting the bullseye. And hitting the bullseye in a laboratory environment means, yes, you've got the correct answer. Now, precision is going to be a little bit different, because now we've discussed this precision in terms of how low can we go as far as the digits go. But precision is also about clustering your measurements together. So if I go back to this dartboard, I'm going to see that in this second example, we've got a lot of darts here that are clustered together. That means that you did the same thing over and over and over and over and over. It wasn't quite right, because if it was right, you would hit the bullseye here, and you didn't. So you didn't get the correct number that you should have gotten, but you did the procedure the same way over and over and over, which is half the battle. It just wasn't the proper answer that you should have gotten with that laboratory experiment or that laboratory data. And then this third example here, folks, you might as well forget it. This is somebody drunk in a bar on a Saturday or Friday night. They have no clue what they're doing. They're just throwing darts all over the place. They're not clustered together. They're not hitting the bullseye. And for a laboratory worker, what this basically means is that you're generating laboratory data, and the laboratory data is hit or miss. You're not getting the correct answers. The answers that you are getting are spread out across a wide range of values. I can't make heads or tails of your laboratory data. And this is what we do not want to be. So in the very beginning, in a laboratory course, there is a tendency to throw your darts this way, and we need to get better. And that's the purpose of our program, and that's the purpose of our courses, and that's the purpose of doing our laboratory experiments over and over that are very similar to each other, because we want to hone in and get you to start throwing these darts a little bit closer together. And in the beginning, your darts might be getting close, but they might not be giving us the correct answer. And that's okay. We're at least getting better. And then finally, what we hope that you can do before you graduate, please, before you graduate, is to throw these darts together and to get me a correct answer. So hit the bullseye when you actually do it. All right. So we've talked about this concept of accuracy. We've talked about the concept of precision and how they're different. And now we know that precision can be regarded in two different ways. Precision can be regarded in how low can we go with the values. The more digits that we have, the more precise that we're saying our measurement is. And precision can also be this idea of a cluster of different laboratory measurements that are kind of hanging out with each other and that are really, really close together. All right. Now comes the term, what everyone hates is determining the number of significant figures. All right. So let's say that I go into a laboratory, and let's say that I make a measurement, and that measurement is in a volumetric flask or a graduated cylinder or something, right, with lines on it. Maybe not a volumetric flask, but a graduated cylinder at least. And then we're going to get a measurement of 3.52 milliliters. And there's a question, and the question says, all right, well, how many significant figures are in this measurement? These should be pretty easy, folks. If they've never been easy for you before, then that probably means that they haven't been explained the proper way. So if I look at this value and I see this number, 3.52, well, that means, yep, these numbers are pretty important the way they're written. I'm going to count 3 digits, so there's 3 significant figures. Okay? That's as hard as these problems need to be. That's all that they're asking you. There's 3 digits here in this measurement, and all 3 digits are very important. This means that the 3 and the 5 were certain values. We know it's 3.5 something, and then the 2 was the uncertain one. The 2 was the one that was rounded off, that we're estimating, and that does get included in the total number of significant figures with a measurement. It's the uncertain plus 1 uncertain digit, typically at the very end. All right, so 3 significant figures in total. All right, well, let's try another measurement. Let's say we go into a laboratory and I make a temperature readout. And the temperature readout that I'm getting in the room is going to be, I don't know, 34.56 degrees Celsius. Okay, so I look at this measurement that's reported, and the question says, how many significant figures do you have? Again, this should be a very easy read. That basically means, look at this, okay? 3 and a 4 and a 5 and a 6. There's 4 digits that are written down. That means there's 4 significant figures there. Okay. That doesn't seem so hard, right? Count the number of digits, but there's a trick. So let's say that we go into a laboratory and someone gives me a measurement of 0.6070. And they say, how many significant figures does this number have? Okay, this should be as easy. But the bane to your existence here, I mean, this problem child that's going to be occurring over and over and over are zeros. Whenever I see zeros, then I'm going to have to stop and think, right? I'm going to have to stop and think, are they significant or not? Zeros are always the ones that we've got problems with. So 0.6070, this is how we treat the zeros. If they are leading zeros, that means in front. You typically don't count them, folks. You just ignore them. And this is a leading zero. That is there for a placeholder. That is simply there to let you know, hey, you better stop. This is 0 point something. And that 0 that they write in the very beginning, it's not a significant figure. It's only there to get you to pay attention to the decimal that they have written on the sheet of paper. So this is a placeholder. It's not an actual number that someone has really measured. So any beginning or leading zeros that happen in the front of a digit, we do not count those at all. Those are only the ones in the beginning. Now, this number has a decimal place, and this number has a decimal place, which means that there's a set of rules that we go by. And the set of rules looks like this. If you get a decimal, and there we are, then you count the first digit after that decimal. If there's a 0 in front, then you count that digit, 6. That is significant. And everything else after that was going to count. Doesn't matter what's written. It doesn't matter how many. Everything else counts. So you now treat that just like we did in example number 1 and example number 2. So you're going to look at this number and you're going to go check, 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 check. There's actually 4 significant figures here. Not 5. We don't count that leading 0. All right. Now let's change this example up a little bit. Let's put a 10.6070. Rules change. This is a little bit different because we're not starting with leading zeros anymore, right? There's no 0 that starts this number. We're starting that number with a 1. So that means that number 1, ding, ding, it's going to count, and everything else after that number is going to count. So 1, 2, 3, 4, 5, 6. That value has 6 significant figures that come along with it. All right. Well, let's keep doing some of these examples. Let's look at 0.0708. How many significant figures? Well, these are leading zeros. I don't count those. I start with the first non-zero digit. Ding, ding. That's at number 7, and everything else after that's going to count. So the 7, that 0, and that 8 is going to count toward my measurement. The others, they're just placeholders. That's not an actual measurement. These are placeholders to let you know this number's really tiny. So 3 significant figures will be in that measurement. All right, 0.007. How many significant figures? So I look at this and 0, 0, 0, and there's our first non-zero digit. It's this 7 right there. That's the only number. So this is one significant figure, and that is it. All right, 21.0400. How many sig figs? Pretty easy. It doesn't start with a non-zero or a 0 number, right? It starts with a non-zero number. It starts with a 2. So that one counts. Ding, ding. And then everything else counts. 2, 1, 0, 4, 0, 0. They all do. So 1, 2, 3, 4, 5, 6. This is 6 significant figures that will be in that number. And then let's say they try to get tricky. 5.80 times 10 to the negative 3. How many sig figs? Well, significant figures are going to be important in this scientific notation type of number, but whatever is written here in scientific notation, that's how many significant figures that you're going to have. So 5.80, look at the value. Don't look at times 10 to the negative 3. That doesn't really matter. This 5.80 will tell you everything that you need to know. And that 5.80, well, it starts off with a number, not a 0. So that number and everything else that's written is going to count. So there's 3 significant figures that are here. This 10 to the negative 3, what that means, if you're not very comfortable with scientific notation, is that that decimal moves 3 times. And it moves to the left. That's why the negative is there. So there's our first move, and we write a 0. And there's our second move, and we write another 0. And there's our third move, and we write another 0. So our decimal point is going to go right there. So this 5.80 times 10 to the negative 3, that's actually a 0.00580. That is what that number is. It's just rewritten in scientific notation. So if you look at this decimal, we can move it to the left or to the right 1 time, 2 times, and 3 times. And we get 5.80. So 5.80 times 10 to the 3, but there's a negative there, meaning that that answer got smaller. All right. Okay, so that is basically how we do the scientific notation and significant figures. Now, the other problem that people have is this idea with zeros that happen in a different type of value, and this is something like 1200. So this has zeros, and normally you would look at this and say, well, you know, this is 1200. It starts with a non-zero digit, so I count that one and everything else after, and you're going to get 4 significant figures here, and then I'm going to do a big that's wrong. That's not the way that this is done. And the reason is because these zeros are a little bit different. So first off, there is no decimal point here. All of those other examples had a decimal point, and there's not one in this number. They didn't write it down. If there was a decimal point, and let's say that decimal point was right there, and it was specifically written as 1200 point, and it just stopped, then we would count all 4 of these digits, and it would be 4 significant figures after that. So that follows the rules just like we have mentioned. It's just a different type of number. So if the number has a decimal, you start with the first non-zero digit, and that one and everything else will count. And that follows that set of rules. It's got a decimal because we put it there. And that 1 counts, and everything else after the 1 counts. However, if we go back and just look at the 1200 as this question was written, there is no decimal point. So what we do in this case is we have to understand that these zeros that happen at the end of a number, if it has no decimal and the zeros are at the end, we do not count those. And the reason is because we assume that they have been majorly rounded, and we can't be for certain that they are significant or not. So what that means is that with a number like 1200, the ending zeros do not count, and I only have 2 significant figures in that measurement. All right. So that's going to be the trick. That's really the only trick that you have to kind of keep in mind when you do significant figures. Otherwise, it's a very blank set of rules that say, very simple set of rules that say first non-zero digit, that one counts, and then everything else will count that comes along. Unless there is no decimal, and if there's no decimal on the number, then we got a problem, maybe. And any ending zero, we do not count. All right, so 2.2000. How many sig figs? All right, that one counts. Everything else after. 1, 2, 3, 4, 5. 5 significant figures. We'll do another one. 0.0006. Decimal. First non-zero digit happens here at 6. Everything else counts. Well, there's only one number, so 1 significant figure. 24,000. No decimal. Okay? The 2, the 4 gets counted. The ending zeros do not, because those possibly could be heavily rounded and we're not for sure. So 2 significant figures are going to be here. 24,000 with a decimal on it. The 2 counts because it's got a decimal. The 2 counts. Everything else will count. And this is going to be a total of 5 significant figures. 0.0350. First non-digit happens here, or non-zero digit happens there. The 3, the 5, and the 0, 3 significant figures. 0.0089. The first non-zero happens there. The 8 and the 9 then count, so 2 significant figures. And then finally, 4.360 times 10 to the 4th. Scientific notation, don't let it weird you out. Everything that they write here will be significant because that number will have a decimal, and that's a 4, and everything else after. So 1, 2, 3, and 4. So 4 significant figures in total. All right, so there we go. There is determining the number of significant figures in a value or a measurement that possibly has been obtained in the lab. Now, the other type of question that you might get is a number that looks like this, and the question is going to say, round the number to 3 significant figures, or 4 significant figures, or 2 significant figures, or 5 significant figures. It will just say, here's the value, round it off. All right, so if I look at this, this is 4 significant figures right now, right? 800.7. The 8 counts, and everything else that follows it counts. So 4 sig figs. So here is the first significant figure. There's the second significant figure. There's the third sig fig. This is where I need to round that number to. So the 7 will make that round up to a 1, and 801 will be the proper way that I round that off. All right. So let's say that they give me a decimal number, 0.06995. And it says round this to 3 significant figures. All right, that's not a big deal. The leading zeros don't count, so 0.0. There is the first digit, there's the second digit, and there's the third digit. All right, so that means I need to round it at that spot. Well, the 5 is going to make that 9 round to a 0. And that makes that 9 round to a 0. And that makes that 6 finally round up to a 7. So 0.0700 would be the proper way to round that value to 3 sig figs. All right, let's look at another. 0.07864. round it to 3 sig figs. All right, so leading zeros don't count. There's 1, 2, and 3. I need to round it at that spot. That 6 is going to be my third significant figure. Does that 6 get rounded up? Well, there's a 4 after it, so it doesn't make it round. So 0.0786 would be the rounded value for 3 significant figures. And then finally, 7.096. We need to round this to 3 sig figs. So 7 is my first one, 0 and 9, there's my third one. This is where it needs to round to. So the 6 makes the 9 round up to a 0, and that makes that 0 round up to a 1. So 7.10 would be the 3 sig figs that I would need for that measurement. All right, so hopefully you got a better grasp of significant figures. Again, it's all about rounding. It's all about obtaining data in a laboratory environment, rounding it off the best way possible. And then in the next video, we're going to have to take a look on what we do when we do calculations with them. So if we've rounded a number and then we're going to add or multiply or divide or subtract another number that's been rounded to it, how do we handle the significant figures with those values? All right. Finally, one more slide before I stop this video. Just some more examples. So here's a value. How many sig figs? Well, there's 2. There's my first non-zero digit, and everything else will count. Here's another one. There's my first non-zero digit. Everything else afterward counts. Here's another one. All of these are going to count. It's a decimal point, so I count everything that's listed, right? There's no leading zeros that happen here. Next one, well, this does not have a decimal point, so that one counts, that one counts, that one, and that one, and that one counts. That gives me a total of 5, but I do not count that ending 0. There is no decimal there for me to do that. And then finally, this last one, bunch of leading zeros here in the beginning. All of those are not significant. Only these 2 here. There's the first non-zero and everything else counts. So there's a total of 2 sig figs with that value. All right. Okay, so in the next video, we'll talk about calculations with significant figures. This is half the battle. If you can do this, then you're one step closer in doing the addition and subtraction, as well as the multiplication and division the proper way. All right, so I'll see you in the next video. And hopefully you'll be significant figure pros by the time that you get there.